So Joseph Coe is also a postdoc at Leach. He is working on ice microphysics and applied machine learning. He's interested in air quality, urban climate, and climate adaptation. He is working on a project here called Using Observations and Machine Learning to Constrain Ice Microphysical Processes. Joe got his PhD in 2022 from USC in environmental engineering. So welcome, Joe, and we look forward to hearing what you have to say.
Thank you. Is this mic good? Want to hear me? Okay.
I don't think it is.
I'll put it closer. Okay, sorry. Is that better? Okay, sorry. Yeah, so I'll try to keep under time. Might skip some slides here and there, but basically, yeah, I'm going to be talking about ice microphysics. I work with Kara Lamb and Marcus van Leeuwenhoek. And I don't know if this is working. Oh, there. Yeah, so this is the outline. Just going to motivate why ice microphysics is important, and then give a brief update in parts 1 and 2 of some active work that I've been doing, and then follow up with some other work that other people are doing within the ice microphysics world, and also some planned work that's in queue, and then wrap up with the bigger picture of how all these moving pieces fit together. So, so to take a step back, why are clouds important and relevant? It's because they have a strong impact on the climate. Namely, they strongly impact Earth's energy balance and also the hydrologic cycle. For example, they will reflect shortwave radiation, but also depending on where they are in the atmosphere, they might also have a greenhouse effect. So there's kind of this trade-off depending on what type of cloud, as shown in this figure, and where they are in the atmosphere and its macroscopic properties, which are determined ultimately by these microphysical processes that are happening at much smaller scales. And we're concerned about this for climate projections because, we want to know in a future climate what's going to happen to the clouds. And there's uncertainty with regards to how we model clouds that's going to propagate to how we do these projections for how clouds might change in the future. And for us in the ice microphysics, we're concerned with these high clouds, these clouds that are essentially composed of tiny ice crystals. So in general, ice clouds are poorly understood. And what I mean by that is the fundamental physics determining the microphysical processes are not fully understood. I'll just read this quote from the latest, or the IPCC AR5 physical basis report. So the role of thin cirrus clouds for cloud feedback is not known and remains a source of possible systematic bias. The representation of cirrus in GCMs appears to be poor, and such clouds are microphysically complex. So just to give you a picture of what I mean when I say microphysics, basically all these processes that are going on inside the cloud, from these warm processes happening down here in red, to the cold ice processes that are happening here, they need to be represented somehow within the climate model. And obviously these are subgrid processes happening at nanometer to microscales, and you have to simplify that somehow into some kind of scheme. And for example, here on this right is a traditional, what we call a bulk scheme, where there's different types of cloud particles classified into like, for example, ice or snow or rain. And there's all these different interactions between processes dictating how these clouds will form and how they evolve or ultimately dissipate or precipitate. So obviously there's a lot going on. And just to give an overview of how these microphysics are represented, there's kind of a spectrum of varying levels of complexity. So starting off with the bulk representation on the left, where there might be a functional analytical form of something like a size distribution with a few parameters, and then going up in complexity is something like a bin, where we have a spectral representation of the size distribution, where the number of parameters now increases proportionally to the number of bins. And finally, to the most complex representation, which is the particle representation, where we track individual particles in a Lagrangian fashion, and those individual particles are evolving. And obviously, this is not computationally tractable for a climate model. So most climate models will use something like this bulk model. But then obviously there's only a couple parameters that you can tweak, and there's a trade-off between complexity and how realistic that is. And to add on top of that, for ice clouds, there's a special issue of crystal shape. Because you know, for a warm cloud, you might have droplets that you can represent as a sphere. But for ice clouds, you can't really do that. There's a thing called habit or ice shape. It's a function of its environmental variables like temperature or humidity. And that changes with regards to like how it's transported in the atmosphere, because it's not going to stay within, you know, one temperature or one specific humidity. So it's complicated to predict the habit and the evolution of that habit. And habit is important because it influences its process rates, its fall speeds and optical properties, and therefore, you know, ultimately things like precipitation and its radiative impact of the clouds at a larger scale. So, and just to give you an example, a recent study found that the ice complexity may induce additional cooling effect of negative 1.1 watts per meter squared. And to put that into context, the CO2 forcing is about 2 watts per meter squared. So that's a pretty large uncertainty that you got there just from particle habit alone. So now this kind of leads into one of the projects that I've been working on is explicitly reconstructing 3D crystals from in situ measurements of crystals. And this is some work we've been collaborating with Albany folks, where they've compiled a large database of essentially cloud particle images from about 13 campaigns over the span of about 16 years. So there's millions of these single particle images. And the pro to this data set is that there's a lot of data, but we're limited to its 2D geometric features. But ideally, in a parameterization, we want to know, you know, its 3D properties, because we want to basically constrain the parameterization with something like a mass size relationship. So the basic idea is that we wanted to try is, can we train some kind of machine learning model that can extract the 2D features from these images, and by doing so have, like, you know, a large observational basis to constrain the parameterizations. And obviously there's no real world data to do that, so we synthesized our own. So basically we generated a bunch of crystals randomly, and I'll just show you how we do that. So we have some a priori knowledge of what a crystal might look like. For example, a bullet rose kind of looks like this. It's kind of spiky with the ball in the middle. So then we could generate a bunch of different crystals with randomly perturbed aspect ratios or bullet arms, and then use this as a means to train a machine learning model. So we have this bullet rosette prototype, but we can also expand to other types of habits. And we have a preliminary data set of about 10,000 crystals, but we're going to expand that if necessary. And ultimately, yeah, we'll make this data set open source and the code available as well, so other people can reproduce it. So just to show you how this might look like in some kind of pipeline, we wanted to test, can we predict effective density just from the images alone? And this was done training on like a couple hundred rosettes, synthetically generated rosettes. So what you would first do is extract some 2D features from random projections of these crystals, and then put it in a tabular form. So you can imagine the inputs are these 2D features, and you want to predict something like effective density. So then we'll train a bunch of these, you know, traditional ML models, these low-hanging fruits, see if they have any kind of, you know, effectiveness at all. And when tested on unseen data, you can see that for a random forest, for example, it had an R-square of 0.9, which is pretty decent. So this kind of gave us confidence that, you know, there's something going on here, and this gave us like some incentive to move forward with some more advanced methods, which I can talk about next. So what we want to do next is do explicit reconstruction. So in the world of computer vision, this is kind of has been a hot topic for the last decade. For example, if you have an image of like a car, can you make a 3D model out of it? So I've been kind of doing a little digging into that literature, and I found this paper in 2016. So this is kind of ancient in the world of computer science, but I wanted to, you know, see, but it was kind of digestible for me. So I wanted to see if I can use this model, right? And I wanted to have like an explicitly reconstructed crystal for today, but I ran into technical issues. So I'll just show you the pipeline of how this is going to work. So essentially, you're going to train with multiple views of crystals. And this 3D R2N2 network is a pre-trained network on a bunch of random everyday objects, but we need to fine tune it, which means you need to train on our specific object of interest, which is crystals. And it's an autoencoder structure with the recurrence model in the middle. And we train that with its known voxel representation. And then once we have this fine-tuned model, you can basically test it with unseen synthetic data. And then ultimately you want to infer the voxelized model from CPI images. And then the reason why this is beneficial is now that we can have distributions of relevant 3D features such as effective density or even surface area or aspect ratio or anything you really want to calculate. And then that can be used in future parameterizations. So this is kind of groundwork, and it seems maybe a little abstract, but it does have connections to parameterizations in the future. So now jumping into kind of part two. So I mentioned the CPI data set, and I mentioned how they're categorized into different classes, and that was done with a supervised CNN. That was done by Vanessa Prizzibolo from University of Albany. But then we thought, can we cluster them in an unsupervised manner? Or, moving forward even more, like, can we learn something about its shape in the latent space? So this is just a really simplified test case. Basically, train a variational autoencoder with CPI images, and then can we cluster in the latent space? And I'll show you a very simple example, the equivalent of a dog versus cat, but in a crystal rosette world. So we are, we want to cluster spheres versus rosettes. So we use 100 images each, and you can see they're pretty distinct. And we wanted to make this easy as a proof of concept, right? So we trained different variational autoencoders from vanilla to implementing different forms of invariance or class conditions. But I'll just show you the results from the vanilla VAE here. And we use 2 latent variables, and we downsample to 28 by 28 for computational efficiency. And you can see here on the left, this is a visual representation of the latent space, and you can see a clear separation between the spheres and the bullets, kind of, on the bottom left to the top right. And here in the scatter form, you can see this even better with the separation between the bullets and the spheres. So we know just visually, like, this is working pretty well, right? With only 100 samples each. Next, yeah. So then we compare to the true labels to something that's done with unsupervised labeling, for example, with k-means clustering. And in the middle is with unsupervised learning. The left is with the supervised CNN. And we see it identified 100% of the bullets and about 80% of the spheres with the false positives bullets with spheres. But this is kind of a proof of concept just to show like this actually works. And I just want to note, this is done without any convolutional layers. This is with fully connected layers. So moving forward, we want to use even different architectures in the VAE. But this is was kind of an encouraging sign. And just to give you some context, so it's like 28 by 28. That's almost like 100 feet or 800 features. But then to condense that down to 2 latent features and to be able to separate out, that's pretty amazing. So we think that there's something going on here. So just for fun, now we included 9 classes of particles, see what happens, right? Same setup. Obviously not gonna work. So next steps are gonna, like I mentioned, change the VAE architecture, play around with that, increase the number of latent variables, and even moving beyond just clustering, thinking about how we can use the latent variables potentially in parameterizations or to inform parameterizations. Because it's not just about classifying, like classifying is a kind of artificial thing, and there's lots of crystals that are in this gray area. So how am I doing on time, by the way?
Yeah, you're good.
I'm good, okay. I'm a little rushing a little bit. So some work that's in the pipeline. So we're also working on some perturbed parameter ensembles, similar to what Linnea mentioned, but in the ice microphysics world. And here on the left is just LES simulations where we got 4 categories of crystals. And essentially what we're doing, just to remind you, Oh yeah, sorry, but just to remind you, the different levels of complexity and the way you can represent the microphysics. We're comparing the bulk, which is the simplest type of representation or the simplest scheme. And then we're going to compare that to the Lagrangian particle representation as a ground truth. And then doing that comparison, we're going to essentially constrain the parameters within the bulk microphysics scheme. And we're using a case study of a icefall field campaign that was done in 2022. So that is going to be starting soon. And just to give you an idea of what some other people are working on. So Carol Lam, for example, has been doing some work using cloud chamber data. So opposed to aircraft data, she's using data from this chamber where they essentially simulate a cloud and then fitting constraining parameters for a Parkland model using the observations from the chamber. And what Carol is showing here is kind of there's like a spectrum of models driven by physical knowledge to purely data-driven models and everything in between. And we also had a PhD student, Jonas McKaylee, who's coming from a stats background. So he had been also doing some work constraining depositional ice growth models with the cloud chamber data, but in a more rigorous Bayesian workflow type of way. So you can reach out to him if you're interested in that. And I believe he's working on a manuscript for that. So to fit this into the bigger picture, what we ultimately want to do is incorporate all these different observations from aircraft, from balloon measurements, lab measurements, and basically iterate with machine learning and Bayesian statistics to constrain the parameters of existing parameterizations, and also looking forward to improving parameterizations overall. So hopefully I gave you a little picture of what's going on in the microphysics world, because there's a lot going on. But yeah, so it's been really interesting this past year, and hopefully can make more progress going forward. And thanks to my advisors and collaborators, and just end with this nice scanning electron microscopy image of ice crystals. So yeah, that's it.
Thanks so much, Joe. Are there any questions here in the audience, starting with the audience and at the Innovation Hub? I have one question with respect to the 3D from the 2D. Is the goal there more about interpreting this the large body of information as sort of distributions more generally, or is the goal there about constraining your PPEs, or like how does that? What is the final goal there?
Yeah, so I think there's kind of different directions you can go with that. So as you mentioned, yeah, understanding the distributions of the 3D features is definitely a first step. But then to also incorporate, like, for example, something like a 3-dimensional mass size relationship into a type of parameterization that incorporates ice habit would be like definitely something we want to work towards.
Yeah, Viviana?
Thanks, that was amazing, and I feel like, okay, now for this year, I get to ask all the newbies questions, so I'm definitely gonna take advantage of this. I was really fascinated by the work that you did with that simple like autoencoding procedure, and like how well you get to separate things in this 2D space, especially coming from a field where we've been trying to distinguish between spiral and elliptical galaxies for like decades, and I don't think we are as far as you are. So did you mention that this VAI VE that you have is not rotational invariant yet?
Yeah, so I tried. Oh, go ahead.
No, I was just impressed because I was imagining that this is something that you have to use, and so I was just curious, why, like, if that's your next step, or if you think that the convolutional aspect will help more.
Yeah, so I did try the rotationally invariant version of that, but I guess maybe for that simple case, it didn't really change anything. But yeah, there are different invariances that we can also try. Yeah.
Do we have any questions online? Okay. All right. I guess I have another question about the 3D, the synthesis. model seems like you did that for the bullet. Is that like a challenging thing to do, or do we know how to do that? Is this one that's kind of like, we've talked about in LEAP a lot about that if we can just get the resolution down, we kind of know how that works. Do we have that down? It's just a matter of we don't have enough computational space to run it in in a big model, or is that another challenge you have to overcome?
Sorry, just to make sure I understand. So you're talking about the reconstruction aspect of
Like
it?
the synthesis of the different ice crystals that you're using to infer the 3D structure. Is that a hard challenge also, or is that like kind of an easy thing you just have to implement?
It is hard for me because it's new. I'm sure if like it was a software engineer, like they, it would be really easy to implement. But it's just like these models are new to me, and just even finding the appropriate model to do that was a little challenging. Yeah.
But Jerry has Jerry Harrington has already implemented a ice microphysics model that uses that geometric model of the budding rosette as a to parameterize how the ice crystal will grow. So it's kind of ready there to incorporate any information that might come from analyzing those in situ data. So it's sort of, that was one of the reasons I think why Kara and Joe went with that, is because it's already sitting there ready to sort of ingest the data.
Yes, that was a great clarification.
Kara, I see your picture has shown up here. Did you have something you want to say? Or
Yeah, I'm just going to add that is also related to the PPE work that we are planning, is that has been now implemented in the super droplet code. So like, but there's this complication of part of the depositional ice. The problem with particularly depositional ice growth is that it is not that well understood, and like especially how to like incorporate all these different ice crystal habits when they're like growing in competition with each other.
okay, another question here.
Very cool, Joe. I was wondering, I guess also going back to those 3D reconstructions, what fraction of that is being influenced by the CPI images, and what fraction is being taken from those like kind of geometric expectations? Maybe I can read, but how do you incorporate those geometric expectations into the 3D reconstruction?
Can you clarify what you mean by geometric expectations?
Just the way that the crystals will form. Like you showed some of the like geometry sketches from maybe one of Jerry's students. Yeah, the a priori geometric.
Oh, I see. Yeah, so yeah, I guess there's since we're training on this a priori assumption, it'll be 100% reliant on that. We're assuming rosettes look like that. So if there's some deviation from that, like for example, if there's a weird rosette, then it might not do so well. Yeah.
Oh, so this part doesn't have any input from the CPI.
No, we're completely training on synthetic data. Yeah. But I guess you could do data augmentation to maybe improve that.
Okay, well, thank you again, Joe, for your presentation. It was great. Give him another round of applause.